My name is Mike Warfe. I'm the Assistant Director for Research Computing and Cyberinfrastructure, and I'm here to talk about our research computing resources that are available on campus. So if you go to our website, you'll see this. The mission of ITS Research Computing is to facilitate cost-effective access to IT resources for the research community at CRU, including HPC, sysadmin services, database design, programming, et cetera, et cetera. A lot of what we do is actually more than that. If we simplify our mission, it's kind of more about providing services and staff to support the needs of the faculty members and their research projects here on campus. We try to do this by a couple different ways. One is to engage, really to focus on what the needs are within the campus, and then help create value by developing new resources such as the HPC, building out cyber infrastructure through working with our network engineers to make things faster and more optimized. We also provide a lot of educational resources by being able to do things such as boot camps, being able to bring in resources such as Exceed or Ohio Supercomputing Center. But fundamentally, our goal is to deliver this education and these services in order to support the mission of this world-class modern research university here at CASE. So if we break down our services, there's really two different components. Cyber infrastructure, which we've talked a little bit about today, and a lot of the different projects that we've discussed this morning have really, we've worked with them to utilize, to really optimize, what they're doing on campus. And then there's also the support component of it as well. So I'm going to talk a little bit about the different resources that we have here on campus. First and foremost is our high-performance computing facility. It's a growing medium-scale HPC system that's Linux-based, based on Dell PowerEdge servers, as well as networking and high-performance storage. It utilizes what we call a scheduler called Slurm, which stands for Simple Linux Utility for Resource Management. And it's basically a first in, first out queue engine that you submit jobs to. The jobs are then ran on all the nodes that make up the cluster, and then you get your results. We have an advisory committee called Advisory Committee on Research Computing that kind of helps, and it's faculty-based, to develop the policies, procedures, and standards for how we allow faculty to receive resources and then utilize them effectively. We make use of Exceed as well as Ohio Supercomputing Center for larger computational tasks because, in reality, we have a finite amount of resources here on campus. A lot of people use it, but we also recognize that there's larger jobs. And when you start thinking about the possible of research and taking it to the next level, having those external resources out there is very helpful, especially because we're looking at resources that you can have startup credits, which allow you to really experiment and try to figure out how to build, how to make your project a lot larger through those resources. And then we also do documentation through a Google site. If you Google or search CRU HPC FAQ, you'll get to that. There's also a portal there on the right side that allows faculty members to basically go to our account management system where they can sign up for resources within the system. So to talk a little bit more about speeds and feeds, the HPC's resources are as follows. We have regular compute nodes. There's about 236 now that sit in our KSL data center. And it provides about 3,200 processor cores that you can utilize via Slurm, which was the schedule I talked about a second ago. We have around 30 GPU nodes at this point, and that gives us around 58,000 cores that you can utilize within the GPU stuff. A lot of the talks this morning have been focused on machine learning and deep learning. GPUs are really critical to that because it allows you to take the data sets that they're utilizing to train those models to actually be able to index everything and then come up with the models that then they utilize for the different research problems. We do have one Xeon Phi node, which is a new-ish architecture that kind of does the same thing in GPUs, but we really haven't seen a lot of traction just yet within that, so we haven't invested too much with it. Behind all of this, and Doug in the prior talk talked about speeds and feeds. So in order to make sure that we have a lot of I/O, we make use of what's known as a Panasys high-speed storage system. That allows us to be able to scale it out, so to add more drives, to add more CPU, and add more networking capacity to basically meet the needs of all those cores, to make sure that there's a balance between how much cores you have to actually compute on versus how much storage you have to basically read and write to. We also provide within our HPC area a Hadoop cluster that has been utilized a lot for machine learning, as well as being able to make use of HBase and the different technologies that we've talked about today. And then we also have virtualization services that are specific to different projects that require kind of an enclave inside the HPC because of the data that they're computing on. So how do you get resources? HPC resources are available to the campus community for free. You just have to be a faculty member. As I mentioned before, just go to the Google site, go to the right side. There's a little login page that you basically have a portal to create accounts there. Additional support and resources are available to what we call HPC members. These are identified by research labs, and they get additional benefits by being able to have multiple processors. So you get kind of a little bit more shares in regards to what you can utilize at the time. This gives you more processors, longer wall time, and larger storage space. Memberships obtained by an annual membership fee or hardware purchases that will be then utilized within the cluster. And as always, we like to try to work with the faculty members to put this into your grants proposals, as well as creating good budgets so that when you're rewarded, that you have the right resources and computational power available inside this facility. So we can give pricing for grant awards as requested. So it's great that we have a lot of storage and we have a lot of compute nodes to be able to do processing as well as storing of the data. But it also requires a network to be able to interconnect all these things. So Doug mentioned before that the common Hadoop node has 10 gigabit network. In order to shift data back and forth between all the different storage systems that are a part of Hadoop, and namely HDFS. We do the same thing within the cluster. We have kind of a basic building block of a rack that sits in the data center. At the top of it, we usually have a switch, and then we have multiple racks that are interconnected. We call that a core network, and ours within our cluster is 40 gigabit. Each compute node that sits in the rack then is connected via 10 gigabit, which we call an access network port. All of our services kind of utilize that framework. So when we start extending out beyond the data center, we also make use of the 10 gigabit network that's provided throughout the campus enterprise network. So that allows us to be able to send and receive data to the labs quite efficiently and quickly. What we've found over the years, though, is that it's great that we can transfer data back and forth across the campus, and there are some pain points that we see, and we try to work with labs to kind of identify them and then build, new solutions to be able to allow them to successfully, navigate the campus network. But what we've really found is that there's been a lot more research driven by, outside of the university. So we've kind of started to develop what's known as a Science DMZ, and that's been integrated inside of our research network so that we're able to accept and as well as transfer out large data sets to our collaborators across the country and even across the world. So the Science DMZ, what is it made up of? So there's 4 key concepts that I want to talk about. First of all, like to give some background, the energy sciences, the physics people, the large, collider that's out in CERN, essentially, they've always had to deal with this kind of stuff of, creating these large, massive amounts of data sets. This is also in the astronomy areas too. And they've needed to transfer it. So they've kind of, worked on this problem for quite some time. And within the energy sciences folks, they're like, we need to be able to show people from the multiple different disciplines that are now seeing this problem because of big data, how to effectively transfer your data from point A to point B. So they really came up with these 4 key concepts that kind of makes up the Science DMZ. It's a network architecture explicitly designed for high performance applications. So usually what that means is that, on our campus networks, you have a lot of web traffic, you have a lot of, multimedia going around because of Netflix and everything else. You really need to have an isolated network that's primarily designed to transfer data from point A to point B. The use of dedicated systems inside of this network is always a good thing too, because those resources are dedicated to quickly transferring data, again, from point A to point B. So you also minimize the amount of firewalls that, usually are there to protect the systems from being hacked into or any of those sorts of things. But you, instead of creating a firewall, you actually harden up the machines that are utilized to transfer data back and forth, or also watch the performance of the network. So that's one other thing that you do in regards to this key concepts. Again, the third one is actually do the performance management so that you're able to know before you start transferring data that if I'm going to transfer something from Case to Berkeley, you can test to see if that path is clean or not through these types of performance systems, which are known as perf sonars. And then obviously the security policies and enforcement mechanisms are tailored to being able to transfer data really, really quickly. This is all coming from ESNet, and if you're more interested, look at this data. If you Google faster data, it usually comes right to this page. So our campus Science DMZ started a couple years ago, and it was from an NSF CCNIE award. Roger was the PI on this. And what it brought was 100 gigabit connectivity between our campus, Ohio's ORANET network, which is Ohio Academic Regional Network, Research Network, I'm sorry, which is a conglomeration of all the schools, the colleges, as well as some middle schools, as well as the state federal agencies. But ORANET itself is primarily designed to allow research data to be transferred between, the large higher ed educational institutes here in the state of Ohio. It also provides us our connectivity to internet too, which is a research network that has not only resources in regards to network infrastructure, because they also have a 100 gigabit network that, is nationwide essentially. But they also provide us other services that we've really started to tap into, such as our Amazon Web Services accounts. So it provided us that 100 gigabit connectivity to internet too, as well as ORANET, but it also provided us the ability to provide a 40 gigabit data transfer node, which is one of the key principles of creating a Science DMZ. So this allows us to very quickly ingest data from outside, institutions or outside public data sets. So we see a lot of utilization actually is within the cancer research. So there's this resource called TCGA, Cancer Genome Atlas, that a lot of our biomedical researchers make use of to be able to, look at variations of different cancer mutations, those sorts of things. So it's a large data set. they really, have driven the utilization of this network and this data transfer node, because they can quickly ingest data into our HPC facility, compute on it, and then basically delete the data after they've done their computations, because they know that they can quickly pull the data back out from the TCGA system. So that saves us a lot of space in terms of storage, but it also saves them a lot of time, because they know that they can quickly get the data back if they need to. We also did a select building network upgrade. So part of the proposal, we looked at the different buildings where we felt like there was a lot of high data volume transfers going around. So a lot of the engineering buildings, the BRB, Wilstein Research Building within the med school, we did some network capacity upgrades to be able to ensure that the data that at least was being transferred on campus would be highly performant as well. That award was about 2 years. I think it closed last year. We wrote a second proposal and was actually awarded for what's known as a CCDNI engineer. So it's a Cyberinfrastructure engineer. Roger mentioned this morning, but the goal of that award is we take it the next step. So we did a lot of infrastructure upgrades. Now this guy or girl that we're going to hire on will be able to take that to the next step, where they'll be able to work with labs and figure out where the pain points are, and then hopefully optimize the network paths as well as even the research projects, so the pipelines that they've established to really, make things a lot better for the research lab as well as the equipment that's here on campus. So in order to do a lot of computation, we obviously have to have a lot of storage. We have a current portfolio of storage services. One is the Panasas that we spoke about a second ago, that really handles the Scratch as well as the home directories that's presented within the cluster. This is kind of deployed within the cluster, and it's not really a service that extends outside of that facility. We also provide what's known as research storage. Today we have about 1.1 petabytes of usable storage that is about at 80% capacity right now utilized to provide data that people need to utilize within the cluster as well as within their labs themselves. So you're able to connect to it via your Mac, your Windows machine, via normal Windows file sharing, or SMB is what we normally call it within the IT side, as well as NFS from within the cluster or actually within desktops themselves. We make use of what's known as snapshot and replication to be able to ensure that the data is available, but also it's backed up in a way that's feasible from a cost perspective. We also provide what's known as Research Archive, and this is something that we've just brought online over the last couple of weeks. And what it provides is object storage, essentially. So people are kind of getting more used to the idea of Amazon S3, or storage that doesn't really fit the normal I read, write, I update, the POSIX sort of stuff that we're used to from working with Windows or working with Linux. So what this provides is a way to upload your data into a repository, and then that data itself can be then migrated to tape per some sort of retention schedule policy that we provide. So this is very attractive to researchers that have a lot of data that they need to keep, but they don't necessarily need to keep it online. So what we can do with this storage is, after it's been uploaded into the environment, we can then cut tapes, and those tapes can then be put off-site. They can be put into a library that sits at KSL that's environmentally controlled, or it can go out to the lab itself. There's multiple policies that we can kind of deploy for this storage, but the idea is that we're trying to provide a service that allows you to archive and retain data that you've utilized for your research projects that may be tied to grant funding, or it may be tied to the paper that you just published in a way that's cost effective, and you only have to pay it up front one time instead of having to pay, on a month-to-month basis. And then finally, faculty members can purchase or lease, these types of storage systems on a yearly basis, or they can pay for equipment up front too, which is very attractive to grant proposals. And then obviously we use multiple sharing protocols such as NFS, Windows file sharing, and Globus as well to transfer the data back and forth from these services. So one of the things that this is kind of the advertisement section of my talk. One of the things that we've been trying to get a lot of the researchers to utilize on campus is something that's called Globus. So this is really a pro tip. Globus gives researchers everywhere access to a powerful data management service that's really easy to use. Basically, if you go to globus.org, let's see if I can do this without messing up the talk. You basically have an online portal that you can then connect what are called endpoints, but these are basically clients that either sit in clusters. So Case has a couple endpoints that you can then utilize all of our storage, but you also have endpoints on your own desktop. So what this allows you to do is log in. I'm not going to go through this process because of time, but it's something that's really nice because you can, with a few clicks, select folders that you want to share with your collaborators, and then they have easy access to it through the web portal itself. Because of the amount of time, if anyone wants to talk about it, please see me at the end of this talk or during the day, and myself or others will be very happy to help you out with it. So we do have a couple more services, and I'm going to quickly glance through them. We also have what's known as the secure research environment. So because we're a biomedical institution here, we deal with a lot of HIPAA. We deal with a lot of other federal regulations, such as FISMA, which is Federal Information Security Management Act, that's kind of attached to a lot of the different grants and contracts that we see now today. So in order to help researchers, we kind of build out this private cloud for processing and storing regulated data. So it's good that we have all this technology, but at the same time, a lot of these different laws also require us to provide a security program around that. So we've crafted our security program around HIPAA because we're surrounded by hospitals, so it made a lot of sense. And in order to be able to be awarded for these grants and contracts, we also utilize FISMA and selected FISMA controls. And these are mostly security controls. So within this environment, we're able to provide virtual desktops, virtual machines, storage space, being able to allow people to transfer data in and out of this environment. And we have a lot of security around network segmentation, being able to do vulnerability scanning to make sure that the data as well as the people that are accessing the data are, the right people to be accessing the data. And there's a lot of consultation that we provide in order to make sure that this service is the right service for you to put your data into, as well as process in. So one other area that's part of cyber infrastructure is data visualization. I won't go through too much of this, but we have specialists on staff that can help you with going from having a data set that has a lot of different facts in it and then building something from it. We mostly work with Visit and Paraview within our HPC, but we also have a visualization wall that sits over in AW Smith that then we can take the data and the models that we've created on the HPC and then show it on a large visualization wall. And then finally, we have research database services too that we can provide. If you have a project that needs a database built from it, we can do that. We mostly use what's known as Oracle Apex for this because it's web-based and there's really no need to install a client or anything like that because you can use your browser. But we also have other services through partnerships with schools and colleges, and that includes a lot of the different electronic data capture systems that are used in the biomedical space, such as RedCap, LabMatrix, Encore, and as well as custom application development that we can provide. And then there's software licenses if you've ever gone to the software center. So this is what it looks like from an architecture perspective. A lot of blocks, a lot of words, blah, 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 essentially. It can get really confusing. To tie this back into what Roger said this morning, cyber infrastructure is a large part about people. Our mission here within the university is to help further the research, to optimize things, to really, kind of be that partner that can look at all the technology, but also understand what you're trying to do in regards to the science and the research. So we're really committed by providing domain knowledge in the technology component, but also in the scientific discipline expertise. As Roger mentioned, at this point we're about 6 PhDs, 11 masters that, have dedicated, part of our, experience to the research itself, but also learning more about the technology and how we can embrace technology to extend, the research. So it's really what I'm trying to say right now is, we're really willing to come to your lab and discuss your needs and help you write proposals, as well as help you find better ways to do, your bench work, but also how that involves the technology itself. We do this not only through, coming to the lab, but it's also the training awareness that we provide through our boot camp that we usually host during the fall. The different training sessions we have in MATLAB, visualization training, and then a lot of the programs that we work with Exceed to kind of provide on campus. And then also concierge with OSC, AWS, and the other cloud providers that we now utilize. So here is kind of our contact information. If you go to case.edu/ITS service-catalog, you'll actually see the depth and breadth of all the different services that ITS provides to the campus. But there's also a section for research computing and cyber infrastructure. Any questions? Great, thank you.